Thank you. Hello and welcome back to Tech Days Online. We've got another great day of content lined up today, and we're going to kick off with a discussion about blockchain. My name is Mike Ormond and I am here with my colleague Johnny Collins. I don't know about you, Johnny, but it feels like only yesterday we were talking about blockchain.
It does indeed. So let's just crack on, get started. There's a lot of content to cover and not too much time. So I'm going to start by just talking quickly about the subject of Bitcoin. Now, Bitcoin, I'm sure you are aware of, has been in the news for both good and bad reasons. Bitcoin is an online digital currency, or aka a cryptocurrency, and it often gets bundled in with blockchain and sometimes even confused with the concept of blockchain. So I'd like to start by kind of differentiating the two.
Okay.
Yeah. So I like to think about this as Bitcoin as an implementation and blockchain more of a design pattern, more of a data design pattern behind the scenes, right?
Okay.
So you could almost say that blockchain is to Bitcoin what a relational database is to something like MySQL. Okay, so it's not an implementation specific, it's generalizing it so we can apply it to other different things, different use cases. Okay, and as Mike likes to call this, I've just referenced magic internet money. Okay.
I don't think I came up with that.
No, I don't think you coined that either. Excuse the pun. So yeah, I'm just at this point just kind of putting no in front of it, a little bit like NoSQL, right? So it's not only about Bitcoin, right? There's lots and lots of other cryptocurrencies, there's lots of other applications for the blockchain and blockchain technologies. So it's important to note that it's not just Bitcoin. And as you can see, I put a little Litecoin symbol in there because I'm pretty clever like that. Okay, so at the moment, if you think about making an online transaction, let's say you want to send some money, let's say £500 to your friend in South America, you would really, the simplest way to do that is go and entrust your bank to do it. You'd go to your bank and say, my intent is to take £500 of my money and give it to someone somewhere else in the world. At that point, you're then trusting your bank to go and execute your intent on your behalf and any other middlemen that are going to be involved in that. And obviously, they're not going to do that for free, so they're going to take some handling fees. They're going to take their little cut of the pie in order to do so. So what Bitcoin and blockchain technologies really advocates is moving away from this model of trusted middlemen to something that we call peer-to-peer. Now, in a peer-to-peer network, it doesn't necessarily mean you're directly connecting to the person that you're actually transacting with, but you are part of a peer-to-peer network where everybody's connected and therefore things can traverse that network to get to where they're intended to go. Okay, and when we're thinking about transactions online and currencies online, there's an issue called the double spend problem that we really need to take into account. And that is, how do you stop someone spending money twice? It's a pretty simple concept. If you've got £10, you can't then go and scan it in and print it out and go and spend it again. So we need to really stop on online transactions of people being able to do such a thing. Now, in the traditional world, there's a lot of counterfeiting measures to stop this, and you trust your centralized bank to actually take record of what money is moving where, and that stops this sort of a scam, I guess. Yeah,
and that's a kind of double-sided thing, because also on the receiving end, I trust my bank to know that they've credit checked you or done the references to make sure that I can ship the goods, and I know that they are going to underwrite that transaction. So we're trying to move away from that model,
absolutely,
I guess, into a trustless or less trusted environment.
That's exactly right, yes. And we need to think about that in this kind of peer-to-peer fashion. How do we actually overcome that? So what we're going to start with is we're going to start with a ledger. And a ledger is literally just taking a record of transactions and storing them somewhere.
Yep.
Okay? And this is what your bank would be doing anyway, but we're just moving away from the central authority doing it to everybody else in the network doing it. So if we look at this ledger in particular, as you can see, there's a transaction between Bob and Alice, but there's some kind of confusing bits in here. We have inputs and outputs, and both of them have a value associated with them. And I like to think of this as kind of almost checks, right? So in order for Bob to send Alice £100, he needs to reference a previous £100 that he has received. So imagine that he's been given a check from his auntie, Margaret or something, which is worth £100. Well, what he can do is say, actually, I need to send Alice £100, so I'm going to scribble out my name. I'm going to change the ID from 0 to 1 and put Alice's name on and give it to her, and now she can spend that. Okay, so you're always referencing previous transactions in order to go forward.
£100 is a very generous sum.
It is a generous sum, maybe some big debts to pay. And then Alice has received this £100, and now she wants to go and send £50 to her friend Mo. So in order to do that, she has to reference this previous transaction, or this check that Bob has given her. Now, that's worth £100, and she only wants to send Mo £50 because she's been a little bit stingy.
Right.
So what she has to do is create two outputs, or two checks from the single check. if you think about it that way.
Yeah.
One of them is going to be worth £50, and that's going to go to Mo and be addressed to Mo. But the other one, worth £50, is going to be addressed to herself. So she's going to give herself some change. Okay.
Yeah.
You know, you go to a cashier, you give her £20 for something that costs £10, you get £10 back.
But now I write a check to myself.
You do, and you can sign that off as well. So she then wants to go and send some money to Pat, and again, it's worth. She only wants to send £20, but she's only got a £50 check. So she does exactly the same things, creates two outputs, one to Pat worth £20 and one to herself worth £30, and we can work out at this point that she has £30 to spend, right? She has a £30 transaction to go spending forward. And we're never actually, calculating that. We're not storing some sort of balance against a name. We can just look at previous transactions to work out how much money she's got.
And presumably, I could reference more than one transaction in my input.
Absolutely. There can be multiple inputs, just like there's multiple outputs, right? So especially if it's a big fund, you'd have to aggregate a few different transactions. Now, there can be some little discrepancies in here. So actually, the value of the output can be different to the value of the input. So if you think about here, she has a £50 input, but she's only spending £40 of that, 20 to herself and 20 to her friend Pat. So there's a £10 difference. And that £10 is going to be collected by the system as what's called a transaction fee. So that transaction fee is really a way of saying to the system, can you hurry up and process this as quick as possible? Okay?
Now that's optional. I presume you're exaggerating that transaction fee for the purposes of...
so £10 obviously...
Seems quite expensive
that's just as expensive as using banks, if not a little bit more. So yeah, that's going to be a very small fee in most circumstances. So let's think about one actor within this network, one person running in this network. So what are they actually doing? Well, what they're going to be doing is running some software that is interacting with the network on their behalf. And usually, if you were talking about something like Bitcoin, this would be called a wallet software. And it would be responsible for managing that person's identity, Bob in this case, on the network. And managing any transactions that they want to make, etc. So when we're thinking about identity, it's a little bit more complicated than it first seems. Okay, so we have this concept of private keys, and a private key is really just a random number, and that random number can be generated from anywhere. So you literally could take a dice and roll it out and come up with a random number and store that as your private key. Now that private key has to stay somewhere that's safe. You need to make sure that you're protecting it. Some people just store this on their desktop machine or on their laptop or whatever it is, but you need to make sure that you're the only person that owns that. And then you have the concept of a public key. So you'll pass that private key into some mathematical function, some cryptographic function, which will generate your public key. That public key can be shared. So unlike the private key, which you're going to keep to yourself, this public key can be shared to others. And then that goes into some sort of encoding algorithm or a hashing algorithm to generate a nicely formatted fixed length string representation of you on the chain, okay? So that when people come, like this one at the top here, when people want to speak to you, Mike, they're not going to call you Mike or they're not going to call it Bob, like in this case. They're going to reference you by this identity on the network.
Okay.
Now, these are all one-way functions. You can't take this address and work out what your public key is, and you can't take your public key and work out what your private key is. But the great thing you can do is you can generate signatures with your private key. So I could give you something to sign. You could go ahead and sign that with your private key.
Yeah.
And then you could give me your public key and that signature, and I could verify that, yes, you signed that, and that is an authentic signature by you.
Yeah, okay.
Yeah, making sense so far? For the sake of this, we're just going to call this guy Bob. It's much simpler, but you just got to realize that it's not that simple under the hood. Okay, so Bob could configure his software that he's running to actually download the chain, and that's where this distributed nature comes in. So anybody in the network could download the chain and have a look at all the different transactions in there. Now they might not do that because they might be a light, what's called a light client. So you don't want to download 30 gigs of data, but if you do, then you can absolutely go and do that, and that makes this a distributed peer-to-peer system. Now he's going to download the ledger and have access to all of the transactions that are happening. You can see what money's going where, etc. But if he was to try and cheat the system like he has here, where Bob has actually created a new transaction on the bottom, which is from Mo to himself, so he's trying to send money to himself from somebody else, this is actually not going to work because he can't sign this transaction on behalf of Mo because he doesn't have Mo's private key, or at least let's hope he's not got Mo's private key. So he can't make these fraudulent transactions. And if he tried to cheat the system in a different way, by using a transaction that has already been spent. So here you can see he's referencing input 0, but he's previously already spent that. And this is the classic double spend problem we talked about earlier. This just isn't going to work because we can see that that transaction has already been spent and that check is gone.
And everybody across the network.
Everyone in the network can see that and won't validate that transaction. Now, what if Bob has to come up with some random transactions? He's like, I want to send £1,000, but doesn't have £1,000 worth of transactions. Well, then he can't spend it. You can't reference transactions that don't exist. So again, you can't just make fake transactions. Now, it's not as simple as just writing to your own ledger and hoping that everyone else will copy it. What you actually have to do is you have to create a transaction object and then broadcast that out to your peers.
Okay.
And that will go through a few different processes at that point. So your transaction, for instance, might look like this one here. And this is just a pseudo transaction. It's not a genuine transaction. So once that transaction has been broadcast to his peers, it's going to have to be first validated, which is just checking the signature is OK, and checking that he has valid inputs that will map to this transaction. But once it's been validated, it has to be what we call mined, and we'll talk about that very, very briefly shortly. So I was showing you the ledger as like a tabular format before, which looked quite nice and it's very easy to understand. But if that's not the way that you would actually store the blockchain, or the blockchain is stored, normally you'd store it like this, something like this. It looks a little bit like a linked list, if you can imagine, made up of a number of blocks in a chain. It's kind of an intuitive name, and they named it quite nicely, I think. But basically, each of these blocks contains a number of transactions and some metadata, which is this headers field here. And that just references the previous block. Now, the integrity of the chain is kept because there are hashes of all these previous blocks, and then you add a new hash, reference to that hash, in your new block.
So you hash the block to maintain the integrity of the block,
Absolutely.
and you hash the part of that hash includes a reference to the previous block to maintain the integrity of the chain.
Exactly. So if someone was to try and go back and fiddle with stuff, the hash would break, and we'd invalidate it. So let's talk about mining and the process of mining. So they're seeing all these transactions flying all over the place, and what they're going to do is pick them up, the unconfirmed transactions. They're going to pick them up, and they're going to put them into this unconfirmed transaction list. Now, this is a priority list, so they're going to prioritize transactions based on a couple of things. The first one being any transaction fees that are associated with them. So if you had £10 on a transaction, it'll probably be fairly high up that list. And also on the age of the inputs to those transactions. So you don't end up with stale transactions just sat at the bottom of the pile. So what they're going to go through a fairly simple process, to be honest. They're going to create a new block. That's going to reference the previous block. And again, that's that integrity piece. They're going to add what's called a generation transaction. And that is just a self-referential transaction. So they're going to say, the system is going to send me some money. And this is the only way that whatever currency is. So if it's Bitcoin, for example, this is the only way that you can actually generate new Bitcoin. It's the only way it gets put into the system. And
this is part of my reward for participating in the mining process.
Absolutely. So this is your incentive, right? Yeah. This is a carrot dangling in front of your face. So then they're going to fill the block with a number of transactions based on that unconfirmed transaction list, and then provide something called proof of work. Now, it's kind of controversial. There's a number of different proofs that you can do, different algorithms you can run. Proof of work, proof of stake, proof of authority, etc., etc. And we'll look at that very shortly next. And then they'll broadcast that block. So they've provided proof. The block is fully formed. They're going to send that out to the rest of their peers, and hopefully their peers will accept that and add it to their blockchain. And then they'll just move on. They'll just go on to the next block and try again and see if they can keep getting these rewards, and that's your incentive to continue mining. So we've got a quick look at proof of work. I don't want to spend too much time on this. So yeah, we'll keep it pretty short.
Brief, yeah.
Okay, so we'll just quickly talk about hashing. So here we have a function called SHA-256. That is a hashing function. It takes a arbitrary input, some fixed length, some string, whatever it happens to be, in this case, hello world. It applies some maths to it and generates this alphanumeric fixed length output. So this output is always going to be the same length, but it's going to have randomized characters inside of it.
Yep, okay.
And you can't go backwards. Once you've got this output, you can't work out what the input was.
So it's predictable in as much as I know it's always going to be the same thing, but I can't predict it ahead of time.
Absolutely, yeah. So then if you were to, these functions are very, very sensitive to different inputs. So if you were to just add an exclamation mark to the input in this case, which is a fairly small change, the output is radically different. And there's no pattern that you can really develop to understand what is going to be the output based on this input. Okay, so it's a nice little distribution mechanism. So then we're going to look at a little bit of logic here, and we're going to go over this fairly quickly. So if you don't understand code, don't worry about it. Spend some time looking at this and try and work it out later. But basically, we're going to pass into the same function, this SHA-256 function, we're going to pass the candidate block header, which is the header from the block you are now mining, plus what is called a nonce. And a nonce is just a counter, basically. It starts at 0, so you're going to start with your block header plus 0, and then you're going to check whether that starts with a fixed pattern. The pattern in this case is 3 zeros.
Yep.
Okay? If it does start with that, then you're going to exit the loop and you're going to continue. And if it doesn't, you're going to sit in the loop and you're going to increment that nonce. So that nonce is going to go 0, 1, 2, 3, 4, 5. And you're going to keep putting that into the SHA-256 function to see if you can find the pattern that you're looking for.
So the purpose of this exercise is essentially a competition. It's you're all in a race to try and solve a puzzle.
Yes.
But why? Why do we need proof of work, proof of stake, proof of what's the
So you need to do something like proof of work to show your investment in the network. Otherwise, if it was as simple as I'm writing a transaction and now I can go and verify that and I can ensure that I can verify that because of whatever mechanism, then you could cheat the system very, very easily.
Right.
So by doing this and distributing it across the network, you're pitting anyone who wants to attack the network against the rest of the network.
Right.
You create a transaction, you want to try and verify that transaction, well, you've got to beat the rest of the people in the network.
Okay.
Okay?
And this also, I guess, produces a random distribution as well. So you can't predict ahead of time whether I'm going to win that race and get the reward or whether anybody else is. So everybody is just trying to get the reward by...
Everybody's just trying to get the reward. I mean, the faster your computer, the better you're going to be because you'll be able to iterate through more attempts at finding this pattern. That's why people have built these specialized machines to actually do it. And there's a lot of money in kind of building those machines. So if you do win and you actually drop out of the while loop, you're actually going to broadcast your block at that point. You'll finish mining, you broadcast your block to the rest of the network, and you start on the next one, right? You're going to go for that incentive. What you need to check in the meantime is, has anyone else beaten me? Okay, and if someone has beaten you, well, you know, tough cookies. You move on, you accept that they've beaten you, you take their block, and we call it the highest blockchain because we think about it as a vertical kind of stack. You take their chain, then you start on the next one. It's fairly simple. So I'm sure some of you are thinking, well, surely you end up in a race condition here. So imagine this is a global system, which it is in most cases. You could have some people in China and maybe some people in the UK both mining, and then 2 of them mine at the same time. So 2 have mined that new block and have found the valid hash at the same time. So the local peers are going to see theirs first because it gets broadcast, locally. Now, they're going to go and copy their local one, and at this point, we've got 2 different versions of the chain, 2 partitions, 2 forks. But eventually, one of the chains is going to get longer than the other because you're not going to simultaneously keep mining blocks at the same time for any length of time. So that will overcome the latency between the different bits of the system, and everybody will match, and there will be consensus in the system. So yes, at any point in the system, any point in time, there could be multiple forks in the system, but they will quickly collapse to one solid truth and then move on.
Yeah, so it sounds a little bit chaotic, but I guess there's a couple of things out of that. One is there's this concept of when can I trust the system?
Yeah.
This sort of committing, and then how many blocks behind am I? And so what's the process for that? What do I need to do to ensure that when I send some money, I know that actually that money has been received at the other end?
Absolutely. So any transaction you think has been mined may well have to be recycled. It may actually, the miners decide, actually, this guy over here has won, so I'm going to forget that I mined your block, and that has to be recycled, go into another pool, and be mined again at a later date. Now, you've got to be cautious of that. They say, especially in Bitcoin, they say about 6 blocks deep is when you can trust it. So if it's 6 blocks deep and it was mined 6 blocks ago, then you can kind of trust that as it's not going to go and change because there's so much computational power that has now happened that if there was another fork, they would have to get a bit more than 6 blocks.
To have an overwhelming amount of
computing
capability to get ahead of you. And a block in Bitcoin is about every 10 minutes.
In Bitcoin, every 10 minutes. We're talking about an hour.
And what we didn't talk about very briefly on that proof of work was why you need to be able to vary the complexity of that. That problem, that challenge that you're given.
So if I didn't have so many animations in here, I would just go back a slide. But basically, the pattern we were looking for was 3 zeros, and we were looking for that. Now, that can be altered because there's a variable amount of computers in the network mining at any point, and you need to keep the hash rate about 10 minutes. So as there's less or more computers, you alter how difficult that problem is by adding another 0 to the pattern, and that makes it more and more difficult.
Got it. Fantastic.
So let's talk about the evolution of blockchain. So when you're thinking of things like Bitcoin and Litecoin and all these things, they are simple asset transactions on the chain. So we think about that as simple transaction recording, and we've kind of dubbed that as blockchain 1.0. I don't know if it's an official term, but we use it in our literature. So then we evolve that to something we call blockchain 2.0, and this is where we add general purpose logic execution to the blockchain. So instead of just storing data on that chain, we're able to run code on the chain as well. And then we evolve that even further to something we're calling blockchain 3.0, and this is where we start to be able to integrate that with other systems, start to leverage cloud services, start to run off-chain assets, and track off-chain assets. And this is a place of research at the moment, trying to work out what's going on.
Yeah, we shouldn't underestimate how difficult a challenge that is to do that in a trusted fashion, so you don't break the fundamental principles of the blockchain, but you can still call out.
Absolutely. I mean, if you're thinking about it, the security boundary is the edge of the blockchain, and if you extend that into just any old random system, like you can't trust that anymore, and it breaks the entire system.
And just in passing, 1.0, you sometimes hear that, certainly Bitcoin referred to as an unspent transaction output or UTXO type system. Those are the kind of 1.0 type systems.
So they're down here.
The terminology being thrown around at some point.
You're quite right. Yeah. So if you hear those terms like UTXO thrown around, then you're talking about 1.0. So Microsoft, again, we're heavily invested in the kind of 3.0 generation blockchain, but we're absolutely supporting versions 2 and 1. We're going to make sure that we really get the solid foundations of this technology to be able to allow our customers to use our platforms to harness it. So again, yes, you might see us talking about some of this, cutting edge stuff, but we're absolutely still looking at some of the fundamentals and making sure you can actually write secure contracts and things like that, which I kind of jumped the gun there a little bit. Okay, so that's all great. You understand the technology. So why should anybody care? Well, there's a couple of characteristics that underpin blockchain-based systems, and they are desirable to some people and absolutely not needed for others. One of those is immutability. Mm-hmm. So if writing an immutable ledger is something of interest to you, so that you can prove the authenticity and the integrity of any records, then that's an important factor. Distributed, so that it's fault tolerant and distributed over a large scale. So any natural disasters, the system will probably stay up. Decentralized, so that there's no single point of ownership, so that if you're thinking about, okay, well, the bank owns this particular network, then can you really trust what's going on in that network? Maybe they can SSH in or something.
And if you think of Bitcoin, I mean, Bitcoin was almost a philosophical as much as a technical proposition. It was all about the move away from having a centralized trusted party and saying, actually, I don't necessarily want to live in that world. I want to live in a world where I can
absolutely
do peer-to-peer transactions in a trusted fashion.
And then we've got openness, and that's that anybody can download the ledger, so anybody can theoretically look at it. Mm-hmm. Now, there are a few different quarks around that where you can do different permissions in the blockchain, so that some people can write, some people can read, some people can't do anything. But again, that's kind of a nuance. Ultimately, we're talking about trust here. We're talking about being able to build a system which is trustworthy so that you don't necessarily have to trust the actors who are in it. Yep. So if you are in a position where you might have people who you can't necessarily trust, or you might have conflicting interests, and you need some distributed technology where everybody can write to it, etc., then you might need a blockchain.
Yes, if you want an audit trail, if you've got a number of different parties involved, if they perhaps don't trust one, they may trust one another, but not 100%. Those are the sorts of things that once you add those together, you're in a mix where blockchain might be one of the solutions that you consider.
Yeah, absolutely.
Just coming back to the beginning, you talked about the sort of history. Blockchain was born out of Bitcoin. I think we need to recognize, give credit that was
credit where
credit is due. It was that paper that was written that described Bitcoin, where all of this is really has come from this. Although people are now getting very excited over the last couple of years about the possibilities that some of this, the being able to run code in the chain, that sort of thing they're going to talk about is opening up.
Absolutely. There's a real excitement around this. It's taken a few years. So Satoshi Nakamoto, who wrote the paper back in 2008. Yep. And then it was implemented around 2009, and then things have started maturing in, but it's really, really picked up pace, and enterprises like ourselves are now getting interested in how can we leverage this technology. So let's have a look at a few applications. We'll do this very, very quickly, and I won't dive into too many of them. But again, currencies, we've talked about Bitcoin, we've talked about Litecoin and all the derivatives of that. They are a great application for this if that's what you're after. Things like smart contracts, and I'll explain them shortly, so don't worry too much about that, but that's really an encoding of some sort of contract and sticking that onto the blockchain so it can be verified. Voting, for instance, so we've had things of voting fraud in the news, but if you were to vote digitally into the blockchain system with maybe a biometric or something like that, that could be immutably stored somewhere, then you know that no government party is going to come in and be able to alter that voting at a later date. And then industries that we're seeing traction, and these aren't necessarily the only industries that are going to leverage this technology, but these are a few that we see interesting use cases in. Finance, obviously a big one, understanding the currency angle on it. Things like healthcare and being able to own your own records and understand how you can immutably store those records so that someone can't go in and later alter anything to do with your the healthcare that you receive or any of your medical history. So what's Microsoft's strategy in all of this? It's all well and good me telling you about the technology. So we actually published a paper called Project Bletchley. It's kind of cascaded beyond a single paper now. This is kind of an entire strategy that Microsoft are taking towards blockchain. And we call it, Bletchley's Microsoft architectural approach to building enterprise consortium blockchains. And we've not really talked about consortium blockchains yet.
We haven't, no.
So a consortium blockchain, other than to kind of mirror it against a public blockchain, something like Bitcoin, where anybody can join the network, a consortium blockchain would be more of an agreement between a number of peers who say, okay, we have mutual benefit in running this system. So there may be 4 or 5 people involved in a supply chain who decide that, yes, it would be beneficial for us to run a blockchain. So they get together and they run their own little system, and they don't have to worry about Tom, Dick, and Harry off the street coming in and being able to write to their ledger.
So drawing the distinction between a public blockchain like Bitcoin, where anybody can turn up, and not only can they transact on it, they can also participate in mining and validating transactions, that sort of thing, to a consortium blockchain, which is more of a kind of closed shop, where we all agree we're going to run this thing, we maintain it, but we also contribute to it and run the transactions.
Absolutely. So we're talking more semi-trusted than completely trustless. So out at the bottom of this paper, I kind of think there's 3 sort of pillars that we should talk about. Partnerships, research and development, and trusted cloud. So I'll just dive into partnerships first. So we've been working with a number of partners, and I'm sorry I've probably not put all the partners up here that we have been working with, but there is a large number of them, to bring their offerings, their tooling, their blockchains, whatever it happens to be, and host it on our platforms, and in some cases actually contribute back into their technologies to improve them. I guess the poster child of this is Ethereum. Ethereum is one of those public blockchains at the moment, which is open source, and it's kind of sitting in that blockchain 2.0 era. So it's adding general purpose compute to the blockchain. And again, that's developed in the open by the Ethereum Foundation. So if you want to contribute to that, you can absolutely go and crack on. And kind of something that I should call out is the Turing completeness of this computational power they're bringing. It's not just a restricted execution set that they're bringing. They're trying to build a platform which can theoretically run any sort of application on top of it.
Because Bitcoin has some sort of computational capability, and I can use that, but Ethereum really is a sort of general purpose.
Exactly, yeah. It's Bitcoin, again, as an implementation, is a very restricted execution set, whereas Ethereum, come and build what you want on it.
And we should say there are other blockchains out there that also offer that general purpose capability.
Really,
it's not exclusive to
it's not
to
exclusive.
Ethereum.
Good call out. So if we just quickly look at Ethereum and what we're talking about in this execution environment, is they have something called the Ethereum virtual machine, and they call this the world computer. But basically, the Ethereum virtual machine supports, like I said, a Turing complete execution set of opcodes, operational codes, and that runs on everybody in the network's computer. And then we have this concept of smart contracts. And this allows you to, like I said before, encode a contract in some sort of code and then have that execute on the blockchain. So for instance, if you wanted to encode a contract which said, okay, when my daughter is 18, I want her to have £1,000 distributed to her from my bank account. I know she'll be lucky to get it, but I'm trying not to give her any ideas. But you can encode that on the blockchain, and then when it happens, the logic meets, things start evaluating to true. That money is
once
distributed.
those conditions are satisfied, then there's an output. There's a predictable output from a set of conditions, and when the predictions are satisfied, boom, the contract.
Yeah. And that can be verified because that's going to execute on everybody's machine in the network. So we can verify that execution process.
Got it.
So that's smart contracts. And you typically write those in a high-level language, which is then compiled down into that Ethereum virtual machine code. And then we've got the concept of distributed apps, which is really just sticking some front end on that. They're kind of just putting some nice view or GUI or whatever you want to call on the front of that application. all that contract. Now you can't just go willy-nilly because this is going to execute all over the chain, so you've got to pay for the privilege to do so, and you pay in the Ethereum's native currency, which is called Ether. And there's the concept of gas, which is a variable price, and you pay per execution of opcode, basically. So that's partnerships. Let's move on to research and development. And there's a lot going on in research and development that I don't know about. You know, these things happen in behind closed doors.
They don't consult you on all these.
No, I mean, I'm still waiting for the phone calls to come through. It's just, but it has, you know, it's long nights at home. So there's a concept of if you want to run execution off the chain, so you don't want to actually run the code on the chain in the Ethereum virtual machine, you want to run it somewhere else, or you want to ingest data into the system from an external source, something like the stock market, for example. There's this concept of oracles, which allow you to do this, but there's no way of verifying where that code is running and what protocol or asecure protocol that they're going to be using. So this could be clear text being sent down to you. It could be running on a system which has malware or that has been attacked and compromised. So there's really no way of trusting this. Yeah. So we've been working, and I guess this is much more in the development phase and the research phase at the moment, but on a concept of cryptlets, and that's a way of building a secure host that can run code off the chain, that you can, you know, it's a tested environment, so you can trust it, and it extends that trust boundary of the blockchain to somewhere else, and it will talk a secure protocol into the chain, so you know that whatever code is running, you can trust it.
And there is good reasons for running code off the chain, because there are some challenges around things like the transaction throughput on blockchain, or the openness of it. If you want to keep some of this private, some of your IP, whatever, you know, there are very good reasons for doing this, but right now it's a real challenge, and we're looking.
It is, and especially when you're talking about throughput, is because everyone's executing, you're at the mercy of the slowest member of the chain. So, you know, if there's someone running a terrible machine, then you're gonna wait for their execution.
You're kind of looking at me when you're
sorry, I mean, your Surface Pro is unbelievable, honestly.
No, I mean, you're looking at me as if
well, I mean, yeah, talking about slowness. Okay, so we'll just move on to the trusted cloud. Now, as far as the cloud's concerned, and in particular we're talking about Azure here, there are a number of different ways that this technology can start to integrate with the cloud. So at an infrastructure level, we're really just talking about, okay, you know, taking advantage of things like compute, storage, networking, so we can get blockchain providers. Exactly. Like if you can run it on any computer, then you can run it on the cloud, and that's what we're talking about here, getting those blockchain providers to bring their blockchain to our platform. And then a little bit higher up, we're talking about services that we've offered. And some of these services exist and some not at the moment, but things like key management. So again, where are you storing your private key, and what happens if that goes missing, or you need to generate a new private key, things like that. Can we take advantage of some of the services that already exist in the cloud? Encryption services for encrypting and hashing different assets. And you know, we also have this big tool set of development tools and app platforms that you can host stuff on as well. And then again, solutions, and this is just talking really about things that, you know, the customers build themselves and bring to our platforms. Vertical solutions, maybe healthcare solutions, maybe banking solutions, whatever it is. Come and host it on our platform. In fact, the customer doesn't even need to know that that's backed by blockchain. They can just come and consume it through our portals. And again, marketplaces, this is really a distribution mechanism for these things. So where do you get rid of these?
It's like in the directory as well, it's like a marketing as well. It sort of puts it out there in front of people once you've built your...
Exactly, that's it. You featured app and you get up there and you get revenue streams through it, and you can do different tiers, things like that. It's all good. So let's have a look at an example architecture. So, you know, it's all well and good talking about this theoretically. So for instance here, and this is, you know, by no means best practice, it's just an example here, that we have some web app, which could be, you know, let's say C# MVC application, and it's going to leverage, well actually let's not say that, because then you'd have to use something like Ethereum, and in here I've used Web3.js. So
just going to backtrack on that a little bit.
Yeah, just roll that back just slightly. So let's say this is a Node application, okay? So this is a Node web app that I've got, and I want to leverage some blockchain technology at the back, and in this case we're going to use Geth. And Geth is the Go Ethereum client. So this is the Ethereum blockchain that
one of the Ethereum clients.
One of the clients. I did say that. So there are others. There are others.
Just emphasising. Yeah.
Again, exclusivity is we're not.
So what's that Web3.js thing that's?
So Web3.js is a library that you can install and use, leverage on your client or wherever it happens to be, which can call into the JSON RPC endpoint of Geth. So it interprets the endpoint and gives you a nice RPC interface.
Okay.
So if you want to start doing stuff on the chain from your server, then you can do that.
Okay.
Okay, I mean, you can, and your web app could just be a standard web app. You're going to use a database for storage, et cetera, et cetera. You can start to leverage some of the other services, and you just have a blockchain component which you're calling into to store things on there.
Okay.
And as you'll see here, we've actually got a bit of a weird thing. We've got two kind of partitions within this, and they are the miners running in different subnets. Because you need multiple miners. You don't just kind of run the blockchain on your own. As we said before, it is a peer-to-peer system. It's a distributed system. You can't just give me a box with blockchain and let's get running and think about it like that. You have to think about who needs to be involved in this network, who needs to be involved in this blockchain. Do the regulators need to be involved? Do my suppliers need to be involved? Do my partners need to be involved? Things like that. Make sense?
Yeah, it does.
So let's talk about developing for Ethereum. I know we're picking Ethereum again as a kind of golden child here. There are alternatives, but it's a good case study, this one. So if you are just developing locally, you could just stand up a virtual machine and install things. So you could install Visual Studio Code, install something called Truffle from Consensus, and something called TestRPC. And I'll just go through those in order. Visual Studio Code is our cross-platform code editor. And that has a plugin for Solidity. Now, Solidity is one of those high-level languages that you can develop smart contracts in.
For smart contracts.
Yeah, and then what you can leverage Truffle to then compile that into Ethereum virtual machine code, and then also to deploy that to a blockchain network.
Okay.
Now, we're leveraging something called TestRPC here, and TestRPC is kind of like an emulation or a kind of local dev environment that you can run. So instead of deploying up to a big blockchain and that contract going wild and actually it's completely rubbish or whatever happens to be, especially in your case, you can demo that locally and try that, and that shortens that feedback loop of how quickly you can develop these things.
That's very much like Azure. Azure is you can deploy to cloud, but you can also, there's an environment on your local machine if you install
Absolutely.
that you can deploy to and save that sort of longer.
Exactly, you really do want to shorten that feedback
cycle
loop.
time, yeah.
So, all it is here is changing the endpoint, and now you're publishing to something in the cloud that's running in the cloud. Again, it kind of looks like the similar slide, the previous slide, where we have one Geth node, which is exposing an endpoint to the public, which we can connect to, and then some miners sat behind, which are protected within a network. And this, I think I do have a nice little button. So, do you like that button? I worked quite a lot hard on that button. So
we've got just less than 10 minutes, so let's see some stuff.
Let's show some stuff.
I don't want to put you on the spot, but I assume you've got some stuff to show us.
Not much. So we host at Microsoft, we host a GitHub repository full of what we call Azure Quick Start templates. So if you are familiar with Azure Resource Manager templates, well, we have a number of different scenarios encoded into templates that you can come and just deploy from GitHub. And a lot of people use them as references to start from when they're doing something. Now, we've got this Ethereum Consortium Network one that's up there. Again, this has been around for about 4 months, as you can see here. And you can literally come here and click deploy to Azure.
That's a template that describes the infrastructure that's going to be stood up as a result of clicking on that button inside my Azure subscription.
Inside, yeah. So this is a requirement to have an Azure subscription.
Are you going to do this?
Yeah, I'm going to do it. But I'll just point out that there is a lot of documentation. I am teasing you, just pulling that carrot away from you. There is a lot of documentation in this and some diagrams about what's going to be stood up and how it's secured, etc. So if you are interested, go and check that out. So if I just click this is just going to open the portal, and you have to then go and put a couple of different parameters in to make it unique to you, and then you can deploy it into your subscription, and away you go. You have a kind of dev test environment for blockchain up and running. I'm not actually going to do that. That's a bit too much work.
It does take a few minutes.
It takes a few minutes, as expected.
It's a very quick way to stand up, and again to either tear it down or remove it again in terms of minimizing cost and getting up quickly. It's very convenient.
It's a very quick way to get started on this stuff. So what I am going to do is I'm going to go to a virtual machine. I've stood up with those dev tools that we were talking about, so things like Truffle, Visual Studio Code, and that Solidity plugin. So this is Visual Studio Code that I've got on screen at the moment. And down the left side, we have this marketplace for extensions, and I've installed this Solidity extension. All this really gives me is IntelliSense and keyword highlighting and syntax highlighting, inside here. But I definitely recommend it as one of the better environments for writing your Solidity contracts. And as you can see, probably by looking at it, is that syntactically this is fairly similar to something like JavaScript or TypeScript as it's strongly typed language. So again, this is Turing complete. So you can have if statements, you can have loops, you can have whatever you want in here. You can define structures up here, arrays, etc. So you can come in here and just write your contracts like that. And then we have the concept of this truffle.js, and this is part of, obviously, Truffle. You can use Truffle to template out a new project. And this is a config file, basically. And inside here, it's defining where my build is, and it's also defining some networks that I can use. So I've got a local development network, which is actually pointing to that test RPC instance that we've got running.
Okay.
And then I've got an Azure instance running here, but obviously remote.address is not a valid address. I'll let you believe that or not. But you could just come in here once you've deployed one and just put in the remote endpoint.
Put an IP address in there and that.
Away you go. So you can put as many endpoints in here as you.
What's that network ID thing?
Network ID is that every, especially with Ethereum at least, every blockchain has a unique identifier. So that when you've got multiple miners and all these things going on, they all know that they're on mining the same blockchain.
Right.
Okay, so it is just an identifier. So when you stand up your blockchain, if you use the ARM template, you need to make sure that you define an ID in there that you're actually going to remember and your clients can connect to.
Yep.
Okay, so you could take something like this high-level language, and if we just pop open the console, you could use Truffle to compile that Solidity contract into Ethereum virtual machine code. And it doesn't take too long. This has already been compiled, so without me deleting the folder, it's not going to do anything. But then once it's compiled, you can come and deploy that to one of the networks. And because I've got an instance of test RPC running in the background here, I can actually just do migrate, define a network to deploy that to, and we'll do development. And I'm going to do reset, because if it is already deployed, you want to make sure that it actually updates the contract which is out there.
Yep.
And that's to take a few minutes to deploy it, but because it's just a local instance, it's going to run a lot faster than it would if you were doing it to a remote blockchain. So that's
you've
just
compiled it, you've deployed it.
Up onto the chain. Now let's say that I wanted to actually chuck sorry, did you have another bit?
No, I didn't. I was going to say, are you going to exercise it? I want it.
Yes, let's go ahead and do that. So in order to do that simply, we can leverage something called console. And this is an interactive, what do you call them, a REPL, I guess, for Truffle, and to interact with test RPC in this case. So if I do this.
So you always have to point at that test RPC instance, which is your development. You've called development.
Yes.
And that's you now sort of connected, if you like, over JSON RPC to the...
Yes, to the local one. So I'm just going to quickly, and they have changed the syntax a little bit locally, so if I screw it up, then that's my disclaimer. Yeah. So I think that contract was called vote off, and then you'll have a deployed instance which you can reference. So I'm just going to grab that, and it's going to say undefined, but I expect that. And now we do ref, and it prints out a whole load of mess.
So that's like the signature and other metadata about that.
Loads and loads of stuff. Actually, there's lots of different interfaces to do with the test RPC instance.
And one of the things is an address where it's been deployed.
That's what I'm going to take. Yeah. Okay. So if you think about other blockchains on Ethereum, contracts have addresses just like accounts have addresses in Bitcoin, etc. But I'm going to be very, very quick about this. So I'm actually going to grab an instance of this by using voteoff.app, and then if I can just paste that in there, that's not the right address, is it? Doesn't look the same to me. We'll just get rid of that.
That's a cut and paste error.
That is a cut and paste error. Let's go again. User error. Okay, that's better. So now we've got this app object, which I can just do that to, and it should print out the ABI. So we have this concept of an ABI. And I mean, this exists in all sort of programming languages, but you don't usually interact with it. And the ABI is the application binary interface. And what it does is it describes the interface to that contract. So if you want to interact with a remote contract that's deployed to the chain, you need one, the address of where it is, and two, the ABI, so you know how to call any of the methods that are on there.
So your contract has got things like get voters, close the vote, move to the next vote, those sorts of things.
Absolutely, it is a voting app, so it's got these sort of functionalities. So if I was to do get current proposal, I think I call it like this. You used to have to do it slightly differently. There you go. You'll see there's a vote between Dennis Taylor and Taylor Swift.
So I can choose between Dennis Taylor or Taylor Swift.
You can do, but in the interest of time, I'm not going to rush you through that. I wouldn't want to.
It's not a difficult choice for me.
Taylor Swift every time.
Yeah, that wasn't the way I was going to go.
Excellent. So I'm just going to quickly fire up this. So again, we've just shown this local development. If I change the output from the local development to the Azure development, we could have done it remotely. So my call to actions, very simply, is if you don't have an Azure account, go and sign up. You'll get a free pass for, I think it's a month or whatever it is, and you can play around with some of this stuff. Again, if you want to understand what Microsoft is doing, go and read what we're doing on azure.microsoft.com/solutions/blockchain. Go and try this template out. It's very simple to spin up. Make sure you spin it down afterwards because there might be a few virtual machines in there. You don't want to cost you the earth. And find out more about Project Bletchley. And that really is where we'll be documenting all the stuff that we're doing around blockchain. And there's been new papers published last week, and I think there's going to be another one pretty shortly as well.
Yes, yeah, fantastic. Wow, it's a lot of ground to cover in 45 minutes. Done an amazing job, Johnny. I want to say thank you very much. I know it's not easy. So thank you for talking about blockchain and giving us a bit of the history and a bit about where we are, what Microsoft's doing, etc. in that space. Wow. What I would say is stick around, don't go away. There's lots more great content coming up after the break.